longtime fans will know that I'm a fan of starting new series before finishing or wrapping up old ones. So I'm starting a new series. And this one's called How to Prove It, because a lot of you apparently really liked my Your Proofs Are Trash series. Episode 3 is probably my most viewed video ever, and it did so in the shortest amount of time. But a lot of people were asking, well, I don't want to just see examples of how not to prove things. I would like to see examples of how to prove things. And so this is the beginning of that series where I go through step by step how to do some proofs. And so I'm going to need your help, not just to drive up engagement in the algorithm. Of course, I want that. Let's be real. But also, in order for me to make the videos that you want, I need to know what you want. So I'm going to do a basic problem in analysis, like epsilon-delta proofs today. But I want to hear from you. What kind of problems do you want me to do proofs of? Like combinatorics, discrete math, graph theory, linear algebra. If there's even particular problems you can suggest to me, please do that in the comment section below, and that will give me an idea of what problems to make for, what problems to solve for future videos. So without further ado, let's get into it. The problem that we're going to try and solve today is we're going to try and prove that the sum of a limit is a limit of a sum. So let's do it for sequences. So the limit, prove that, let's say if these two sequences, that's my version of writing an ampersand, an and symbol. If both of these limits exist, then the limit of this sequence of the an plus bn is equal to the sum of the individual limits. So how do we provide a formal, rigorous proof of this? And what I want to do in this video is I want to carefully delineate between the problem-solving process that we'll take in order to come up with the proof versus the actual good copy of the proof. So everything that we do on this digital blackboard here is going to be all completely rough work. And what we're actually going to do is I'll physically take you to talk, well, not physically take you, but it's not a threat. I'll take you to Overleaf. So this is, I'm not going to give you an introductory, like how to go to Overleaf. Basically, just go to the website, make your own profile. This is like, if you make a new project, this is what it will start you, like this is the default file it will make for you. So I haven't done anything here, right? I literally made a new project. It was automatically populated from here. So we'll just work with this completely basic package in Overleaf. Okay, so let's start. How do we actually go about proving this theorem? So let's think about what it is that we're trying to prove, right? We're trying to prove that the limit of some sequence is equal to the sum of two other limits, right? Well, let's try and unpack. I mean, the limit has a formal definition, right? So we should probably unpack that formal definition. So what does it mean? What does it mean that if this converges, right? So the limit, right? The limit is equal to n, or here the limit is equal to b. Maybe I should say, as a slight augmentation, maybe a slightly better way to write it would just say if the limit exists and is equal to a and the limit exists and is equal to b, then the sum is a plus b. Just a cleaner way to write it, right? So let's take that as our statement. So let's unpack, what does it mean? What's the actual formal definition here? If we're going to give a formal rigorous proof, we're going to need, we don't necessarily for our audience, a TA that's marking our assignment, we don't need to repeat the definition necessarily word for them in the good copy. But what we are going to need to do is know what the definition is and work with that, right? So in our rough work here, it will probably be helpful for us if we remind ourselves what the definition is. So it says that for all epsilon greater than 0, there exists a big N in N such that little n bigger than big N implies that AN minus A is less than epsilon, right? Likewise, we should maybe unpack, it's going to be a very similar thing with Bn. Some things are going to look a little bit different. So why don't we introduce some slightly different terminology then, because we're going to reuse some of these symbols. And one thing we're going to want to avoid, because we might be using the definition for AN and the definition for BN, we don't want to get confused with the different kinds of symbols that are there, right? So maybe we could call this epsilon sub 1 and epsilon sub 2, and we could call this n sub 1 and n sub 2, right? Of course, it shouldn't be too confusing. You should be able to parse both of these things and separate those variables, know when it's, an abstract variable versus a concrete one, but let's just be safe, give these things different labels. Maybe it will help us keep track of this information. So it's almost the exact same statement, right? We'll just choose some slightly different variable names and write it as such. Okay, great. Now we also have a third limit, right? We have this limit of AN plus BN. So what would that look like? Again, we'll just implement, a third sort of definition here. Give everything a label. And here you'll notice in this case, so let me write AN plus BN, and I'll put that whole thing in parentheses, minus A plus B, I'll put that whole thing in parentheses, strictly less than epsilon sub 3. Now, you'll notice in this case I did not decide to call N here something different. There it really is kind of working as just a dummy index or variable. We could give it a different name. But here I think it's more comfortable to leave that as open. Remember, of course, this is all rough work, right? This is us just trying to figure out the proof. So, okay, so the thing that we're trying to get to, right? So we know we're assuming that these two limits exist. So we know that both of these statements are true, right? That we can choose we know that there's some real number A and some real number B for which these complicated statements hold. Okay, and the thing is, so those are two statements that hold. That's like what's in our toolkit. The thing that we're after, the thing that we're trying to prove is this statement below, right? This is the goal that we're after. So we need to prove this statement. So let's think, how do we prove that statement? Well, we're going to need to, this is a for all statement, right? So we're always our proof. So let's say in blue, this is going to be our like rough attempt at constructing a proof. Like gut reaction, just say let epsilon 3 be bigger than 0, right? Anytime you see a for all symbol, like that is how your proof is beginning. You're choosing an arbitrary element greater than 0. You don't even need to think before you do this, right? So let epsilon be bigger than 0. Now, the problem is here there's an existence proof, right? So what that means is it's up to us to construct such a natural number or maybe not construct an explicit one. Sometimes we'll need to, right? Like say we choose the number 5 and that works. Probably this is a more general statement. So what it's going to look like more, instead of giving a particular number, it's going to look more like us giving a particular recipe that guarantees we can always come up with the correct kind of number, right? But we haven't really done any thinking. We haven't done any exploring yet in this proof. And so we don't know. We're going to have to do something like define n3 to be, and let me just put a dot 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 for now because we don't know. We haven't started thinking yet. But the onus is on us to come up with this n3. And then the point is, whatever n3 we end up choosing, we're then going to have to do another let, because this is kind of like a for all symbol, right? It's saying like anytime n is bigger than n3, so we'll go dot dot dot. Then, so now suppose. Another way to say this is we're doing an if-then statement, right? So how do we prove an if-then statement? We have to begin by assuming the antecedent, as it might be called in a very fancy term. So we would suppose that little n is greater than or equal to n3, and then we know that dot dot dot, we have to provide, here are our details that are still missing, and somehow we have to get down to this conclusion. an plus bn minus a plus b is less than epsilon 3. Okay, so we have a rough proof sketch already. We're quite a ways away from having the actual rigorous proof, but we've got a proof sketch. Okay, so how could we try and do something here? Well, let's go back in and think again about our assumptions. I forgot to label one of my epsilons as epsilon 1. There we go. So think about these assumptions. Well, we could have, we're allowed, so this for all statement here says that we could make some choice of epsilon 1 and epsilon 2 and have these statements work out, right? So we can basically make this happen for any epsilon 1 and epsilon 2 that we could possibly desire, right? And so is there a way to take these two facts and somehow combine them in order to get something relevant to our goal? So is there some way that we could take, an minus a being less than epsilon plus 1 and bn minus b less than epsilon over 2 and somehow turn this into information about this essential step, right? This is the final step that we're ultimately after, right? Well, one of the basic things that would be covered in a class on analysis, probably if you're doing this, you might have even talked about metrics and metric spaces first. One of the most fundamental things there is the triangle inequality. And so, indeed, notice that if we had the triangle inequality, what does that tell us? Well, it tells us that an minus a plus bn minus b in absolute value is going to be less than an minus a absolute value plus bn minus b absolute value, right? But now, here's the important realization. This term here, if we rearrange it, that's exactly the term that we're looking for. So minus a plus b, that's exactly this term. And this term on the right here, well, we know that we could choose, we know that this term here, maybe I should move over my inequality. This term here is less than epsilon 1. And remember, we have in our toolkit these other theorems. So we're allowed to pick the epsilon 1 and the epsilon 2 to be whatever. So we have that epsilon 1 in our toolkit. We have this epsilon 2 in our toolkit, right? And so, in other words, if we started here, rewrote this statement like this, and then used the triangle inequality, we could come to the conclusion that this thing is less than or equal to epsilon 1 plus epsilon 2. And our goal was to get this term on the left here to be less than epsilon epsilon sub 3. So could we somehow cleverly pick epsilon 1 and epsilon 2 in order that they produce this number epsilon 3? Well, yeah, remember, we're allowed to pick epsilon 1 and epsilon 2 to be whatever we like. So of course we can pick numbers that will sum up to that. Now, how exactly do we do it, right? Because you might think right away, you could say, oh, well, just pick epsilon 1, pick epsilon 2 to be whatever, and then pick epsilon 1 to be epsilon 3 minus epsilon 2. But that doesn't really work, remember, because this has to be greater than 0. So what are some other ways that we could possibly split up that number epsilon 3? There's a lot of different ways we could do it. I think a pretty straightforward one is if we just take epsilon 1 to be epsilon 3 over 2 and epsilon 2 to be epsilon 3 over 2, right? Then when we add these two things together, we get epsilon over 3. Okay, great. So let's try and keep track of this in our toolkit, right? So we know, right? So since these are in our toolkits, we can just simply take epsilon 1 and epsilon 3 over 2 for both of these values. And then our toolkit says that we know we are guaranteed that we can produce some n1 and n2 that make these following statements hold, right? So let's write something down about that. So since, maybe I'll go back to blue for a moment here. So since epsilon 3 over 2 is larger than 0, by assumption, by our limit definitions, we can choose n1 and n2 in the natural numbers such that, well, little n being bigger than n1 would imply that an minus a is less than epsilon 3 over 2, and little n bigger than n2 implies that bn less than b is less than epsilon 3 over 2. Great, and so we know we already argued up here. We figured out that if we had that, then we can argue that this term we're interested in is going to be less than epsilon 3. And remember, that was the goal. That's the thing that we're after, right? So somewhere in this argument is basically all the stuff below, right? But there's another problem here. We had to choose, right? If we look at this step here, so how did we guarantee that these two terms were going to be less than epsilon 3 over 2? Well, we had to pick an n1 and an n2, right? It said, okay, I can grab an n1 and I can grab an n2 that guarantees that both of these things are true. Okay. But the problem is, if we go back to our proof sketch, right? How are we supposed to prove this? We're supposed to define just one number, n3. And we want to make sure that whenever little n is bigger than n3, then our conclusion follows, right? Well, we know, so what do we need? What do we need to get there? We somehow need to make sure that little n is bigger than n1, and simultaneously, that is at the same time, it must be bigger than n2. How can we accomplish that? There's various different ways, right? n1 and n2 are both positive integers. So we could say take n bigger than their product, or we could take n bigger than their sum, for example. These are answers, these are choices I've seen made by students in their analysis homework when I've graded their assignments, and these are perfectly acceptable choices. There's nothing wrong, you can go ahead and do this. But I would say there's also, it's good to be minded towards doing things in an economical fashion. So what is a way that we could do this as minimally as possibly, right? Because certainly n1 plus n2, this is a smaller sort of choice of number in general. It depends what numbers they are, but then the product, right? The product's going to grow really big. And we might care about this. I mean, one is a matter of elegance, right? As a matter of, yeah, it's good to maybe have a conservative approach in some sense. Why use more material than you need to? But also, it could be argued, say, from a practical standpoint, right? Sequences and series, these are very much things that come up in applied mathematics in the real world, right? We want some sort of approximation. You don't want to have to go out to 300 terms to get a decent approximation, right? We'd like to, keep the number of digits we need to keep track of our data and information. We want to think about making things small and efficient, right? So one way we could accomplish this is by taking our n3 to be the maximum, right? So it will just be whichever one of these two are bigger. So that's going to be our plan, right? So if we go up to our proof sketch, somehow, okay, there's a step in here, right? Because I started with this. Now I need to build my n3, right? I need to talk about, it's the maximum of n1 and n2. But if I wrote that next, that wouldn't make any sense, right? So we've done all our rough work below, but remember what's in blue here, this is our actual sort of rough copy of our proof. What do you mean take the max of n1 and n2? We haven't defined n1 and n2. So, okay, we know we have to do this little step in between, right? So this is maybe going to go a little bit lower in our proof, right? It'll go here. And somewhere here, first in our proof, first we need to get our n1 and n2, right? We need to do that thing that we constructed. So here is where we would say, like, by definition, since the limit of this sequence is a ... and we say the same thing with b, right? We wrote this down below. So that should go next in our proof. Then we define n3. Then we suppose that n3 goes here, and then here is going to be our mathy calculations. Okay. I have no idea if this was a better way to explain things. Maybe this is a more confusing way to explain things than the whole proof. But this is some of, scatterbrain thought process. This is kind of what your paper should look like when you're actually doing this. You should be experimenting, playing around. You got to think about things like you're a scientist, right? The paper is your laboratory. You just got to write random stuff down and experiment with it. This is the only way to come up with these proofs. That's it. So let's go over to Overleaf. We have our proof sketch here, right? Let's go over to Overleaf. Let's try and write up this result nicely. So we've gone over to Overleaf. Again, this is exactly what Overleaf will spit out. It's pre-made document. There's nothing to do. You should be able to get to this point. Of course, it'll give you a different author name here. So I would go begin theorem. And you can either type begin theorem, end theorem, the whole thing. But Overleaf is so nice, it even predicts what theorem you're going to use. Oh, I wonder, does it actually have the theorem package? Okay, it doesn't even have the theorem package. We're going to, I guess I'll teach you some Overleaf in this video as well. So, theorem package LaTex, right? So if you want to use some nice feature, okay, maybe we click here, our first result in Google, and it will tell us, we want to use something like this. New theorem. Okay, so we're gonna have to maybe add some things to our document in order to make that work. So Control C. How to prove it. We'll put that in our document. Very important. This goes before wherever the begin document line is. So let's see if that worked. Let's see if that allows us to write our theorem statement. Yay! Now we have theorem 1 labeled in our document. That's great. So let's populate it. So again, let's try and write, formally, what is our statement? Suppose, gosh, what should I call it? Let's go really formally here. So A1, and if these commands are quick for you, you're not sure what I'm writing here. Well, just was my microphone too loud? I talk very loud. If you're not sure what commands I'm writing here, you can just follow along. This is a great way to learn some of these basic commands. So suppose these two things are sequences, and let's say of real numbers. Let's be really specific. Of real numbers, and let A, B be in math BB R. That's how you make the real numbers, such that, and let's make our two expressions. So the double dollar sign will make, we'll just make our displayed equations go in the middle, and I want to space both of these out. So what I can do is I can use some of these slashes here to insert a bunch of space. There's other nice ways to do it. We could use align mode to make these equations aligned. Arguably, that would be a better way to do it. But let's just see. And it got angry at me. It got angry at me because it doesn't know what math BB is, right? I'm trying to make the real numbers. By the way, here is dtextify. Here's a pro tip if you're trying to learn. And I'll just show you. So I'm not going to use my pen. Okay, I'm just going to draw with my keyboard. So you don't need a drawing pen or stylus. You can just use this and draw the symbol you're trying to get. So I'm trying to make a symbol for the real numbers. And you can see it's guessed. It's kind of guessed incorrectly because I drew it weird. So symbol not in the list. Show more. Yeah, show more. I'm trying to get the ordinary real number symbol. My writing is so bad. It doesn't know what I'm trying to draw. So I'll try and draw it again. It was close. Let's see if my drawing was better this time. Not quite. So it should be math mode. Maybe it is this package. Well, this wouldn't be a real tutorial if it went wrong. But okay, so I think I know the answer here. This looks more like Blackboard bold that we're after, right? So use package AMS sim. That's probably what we want. So I'm going to copy that. And let's go back over to our theorems of proof. Again, I want to make sure I put this somewhere before my begin document line. So I'm gonna put it up here. We can talk about ways to organize your preamble, as it's called. That's the term for everything before the document. Yay, and now it works. Look, I have a real number symbol. Great. Okay. So let's finish writing our statement. So we have these things. Then what? Then, and let's write our statement. So we'll go limit n approaches infinity of an plus bn equals a plus b. And we'll put a period there. Punctuation, it's the end of a sentence, it's the end of thought. Great, that looks great. This does look a little bit ugly to me. I would say there's two other options. Those could both go in line mode. So we could go something. So I could just do the single dollar sign. So like this. Let's get rid of this. And this. Oh, by the way, you'll notice I put these little percentage signs in here. This just helps me. Nothing appears if you look at the right side of the document. Nothing actually appears there, but I like to put it in between just because if you don't put that, it will create an extra amount of space, and I don't actually want that to affect anything in the document. But I just find using this command, which is also the command you use to comment out stuff. But just putting one of those there, it helps break up the document in the actual text file. And I find for me, it makes it easier to read through all of those things. So there we go. So that's our theorem. Now we want to make our proof, so I will write begin proof. And again, maybe I forgot that overleaf will just suggest how to end things for me, so I'll just manually type in end proof here. Great. Okay. So now we have to go back and do our actual proof. So let's remind ourselves, how did that structure go? So the proof, right, it should start, very first thing, it should be let epsilon 3 be bigger than 0. And here's another thing where, okay, we made some notational choices. That would help, ease our discussion, but there's not more than one epsilon that we actually refer to in the body of this proof, right? We just sort of use the epsilon 1 and epsilon 2 when we are figuring out what to do, but everything just depends on this epsilon 3. So maybe to make our notation a little bit cleaner, we could just call it epsilon. So let's go ahead and try that. So I'll go back to my overleaf. So we know the very first thing we should start off with is let epsilon be bigger than 0. Great. Now, we needed to somehow get our n1 and n2, right? So, and technically you don't need to mention the step, but I think it's worth mentioning, right? I say the since, epsilon over 2 is greater than 0, right? Because strictly speaking, what does the statement say? It says if you start with a number that is greater than 0, then you're allowed to do this thing. And I should point out the n1 and n2, probably that is notation that we should stick with because we do have two different symbols. I tend, this is a matter of personal preference, to prefer using just distinct symbol names, if possible, instead of using indices, because indices can really proliferate. It depends on the scenario, though. I think there's really good times and places where one could use the subscript. So let's do that. So since epsilon over 2 is bigger than 0, and we could even, so if we really want to drive home all of these details, I mean, you'd be forgiven for being a little lazy and rewriting this, but let's just write both of these things because we're using the fact, we're sort of using these limit parts in our proof. So since epsilon over 2 is greater than 0, and both of these limit things, by definition, we can choose, say, n and m in the natural numbers such that, so let's just compile and see what that looks like so far. Oh, it yelled at me again, but why did it yell at me this time? Probably because I misspelled something. So let's see. Everything looks good in our code. This is great, by the way. It is important to have issues happen live. Does it not like the begin proof command? Is that part of it? Environment proof undefined. So I'm going to cheat a little bit. And I'm just going to tell you that I think we need AMS math package. So this is also how you learn things. So I've given you some tools about how to figure things out on your own. But, as any good instructor, sometimes I'll just tell you, I know this thing because I know this thing. So AMS theorem, and maybe let's put in use package AMS math as well. See, Overleaf even suggested it because it knows it's good packages. So let's try and recompile. Great, now everything's working. By the way, just to aid your own problem-solving process, you could type in something like, Overleaf, why won't my begin proof compile, right? You could check this. Problem with proof environment, right? Here's a LaTex Stack Exchange, and you can find all sorts of great stuff. People, put their code in, and there's discussion. Someone will be able to help you. So that is another way that you can help yourself in these cases. Great. Okay, so where are we in our proof? So such that now I'm going to teach you a nice little trick. It is align mode. So again, I like to put these little $ spaces, just help space out these equations. I will go begin align, so you can see overleaf is suggesting commands. I'm going to do align star because if you don't do align, it will number the equations for you, which is great. There's no problem with that. But this isn't going to be a very long or complicated argument, so I don't really feel like I need to number my equations for referencing purposes. So let's go align star. And we're going to write out those implication symbols, right? So little n greater than n1 implies, and I want to make things line up. So maybe I'll go implies, and that's where I'll put my lining up symbol. An minus a is less than epsilon over 2. You do a slash, just start a new line, and again, I'm going to put the nice little % sign there in order to make just, again, totally, it won't do anything in the compiled document. It's totally just for readability purposes. And I'm going to be lazy, so here's a trick. Get used to using copy and paste, right? Oh, I made a mistake. This should not be n, it should be m. Right? But if you got a bunch of lines that look the same, but you just need to change a couple variables, just write this a to a b, and that's basically it. I think that's very helpful. So now let's take a look. Let's compile that code again, and let's see how our proof is looking. Fantastic, great, and that is mostly lined up. It's a little off there because the symbols look a little different, but that's not so bad. It's maybe a little annoying. There's some tricks we can do to fix it, but let's go on and try and finish our proof. So what did we do? We needed that n and m. And I wanted to define, I've maybe picked a bad naming convention. I maybe should have stuck with n1 and m2, but hey, that's exactly how proofreading grows. And this is the great thing about doing things in LaTex or on a computer, is that if you decide something might be a little bit better halfway through writing the proof, it's very easy to go back and just change your variables. But I'm going to stick with these variables for now, and we can work on editing the proof at the end. So now let's go back. Let's take a look. What did we do in our argument? So by definition, okay, we grabbed our n and our m, and then we wanted to define, okay, n3, I guess let's call it P, capital P, because again, we'll avoid the proliferation of indices. Next thing we do is we define that to be maximum. We then had to suppose little n was bigger than n3, and then we did all of this sort of math down here using the triangle inequality. So let's go back. So define, say P to be the, what is going on? To be the maximum of n and m, right? That's complete step, complete sentence, may as well put a period. Now let n be greater than p. Then, now, what did we really want here? We wanted to get our, we wanted to make use of these equations. So namely this, where now, of course, epsilon1 means epsilon over 2, and this equation, right? So why don't we just say that? Why don't we just reiterate that from the above? And so maybe actually, so here's another thing. Maybe for align mode, maybe I actually want those equation numbers after all. Why not? So then n is greater than, little n is greater than n, and little n is greater than m. Hence, by equations, let's say 1 and 2, we have little a n minus a less than epsilon over 2, and little b n minus b less than epsilon over 2. Now, one thing we could do is try and string all of these computations together. So there's a couple different, ways you could do this. So I like to start from, this on my left-hand side and go through all these steps to end up at my conclusion. So that could look a number of different ways, right? It could look like, starting with, right? This is the term so if we go back up and look at our definition, this is the term that we wanted to show is less than epsilon, epsilon, we're just calling it now. And we could do different things, right? So we could say this, and then let's say rearrange it. And then next in our argument, we could say that this is less than or equal to this term. And then maybe in the LaTeX document, we could say something like by the triangle inequality. Right? So we'd have an explanation of our step right at that step. And then say, this would be less than epsilon over 2 plus epsilon over 2. And then have an explanation beside that of saying like by equations 1 and 2. Say. That would be a perfectly acceptable way to do this as well. I'm just stylistically going to make the decision to, since I've already used equations 1 and 2 in my argument, I've sort of gotten some equalities using that. I'm going to simply mention that we're going to use the triangle equality ahead of time. I will use the percent sign to make a little space. This time I really don't think I'm going to need to label my equation, so I'll use a line star, and I'll start with the expression that I am trying to show is less than epsilon. And of course, I'm going to really go step by step here because I want to make life as easy as possible for the reader. This isn't a very long proof, so I don't. I'm happy to leave a couple extra steps here, so I'll go slow and I'll really show those extra steps each part of the way. Notice I also like to put this little $sign in here as well in the middle of the steps. Again, just helping break up the equations. And let's go here. We could do, now we want a strictly less than, and we could use a frac epsilon over 2. I think sometimes if it's an uncomplicated expression, it's perfectly acceptable to do something like this. Although definitely more so, this is something I would say do this in just an epsilon over 2 like this. If you're in inline mode, maybe it's a little bit nicer, debatably, if we're in some sort of display mode, alignment mode here, to go like epsilon over 2 plus epsilon over 2. And then, made a little typo. Very kind of Overleaf to start shouting at me immediately so that I don't mess that up. And there we go. That's what we wanted to show. Right? So we can end the proof even, just to add a little exposition. Therefore, by our arbitrary choice of epsilon, we've demonstrated, or don't use abbreviations, especially for typing. There's no need to. We have demonstrated that the limit as n approaches infinity of an plus bn is equal to a plus b, and put a period. There we go. There is a proof from start to finish. Oh, and you can see it gets cut off a little here. One thing I would do, this is maybe the grosser option, if you do a double slash like that, it will start a new line. Not bad. I would maybe, even sometimes, even if it's maybe like egregious to do such a thing, I'll put it in display mode, just to avoid it being cut off. And you know, it kind of makes sense anyways, because this is the display mode, right? This is the thing we wanted to show. It's a big focal point, so not a big deal. So there you go. There's an example of taking a proof right from, conception, from our rough work. This messy, chaotic way of coming up with it. So let me know in the comments if you want to, what kinds of proofs you want to see more of. Do you want to see more analysis, topology, discrete math, graph theory? What sort of things do you want me to walk through in excruciating detail like this? But now you have some idea about how to prove some basic things about sequences. So I'm going to encourage you to go off and prove some things.